So welcome to this hands-on session on ROMS modeling. So what I propose to you actually is to take a note of this link here. So this is a link to the slides, and so then you will have any other links as well. So that's https tinyurl.com JuliaEO 25 ROMS. So if you had taken note of this link, you will have access to all other links that are in my presentation. And for the hands-on session, actually, I already prepared for you a notebook server where you can log in and then run all the notebooks there, because the environment is already set up. Okay, and so we don't lose any time to install things. And ROMS is quite easy to use on a Linux machine, where you can install all dependencies via the Linux package manager. But on Windows, it's probably more complicated. Okay. And in order to gain access to this notebook server, I have now here a list of usernames and passwords. Okay. So you can just claim one username by putting your name in another column, or just putting 3 X's. So just to avoid that different people use the same username. Okay. So if you you can also take a picture of this sheet to have the password with you. Okay. So here is again the address to the slides. Okay. So we will speak today about ROMS, which is an ocean model. It's a free surface ocean model, and meaning that you can also simulate things like tides. Yeah. Unlike some model which have a fixed surface, which allow them to have a larger time step. It is hydrostatic, so we have seen this morning also oceanograms can solve the non-hydrostatic equation, which is quite interesting. But at the scales that we are looking at, hydrostatic is generally sufficient. And it's also written in the flux form, meaning that you have naturally properties like conservation of temperature, conservation of salinity. They are essentially for free. And the vertical coordinate system actually follows the terrain. Okay. Yeah?
Also, momentum equations are always in flux form.
Yeah, exactly. Yeah. Momentum equation also in flux form. Yeah. And the horizontal grid is an Araka C grid, so meaning that not all variables are exactly at the same location. Okay, so we'll see that temperature, salinity, and density are defined in the center of a grid cell, and parameters like the velocity are shifted relative to the center. And this is a really neat trick in fluid dynamics, which allows you to effectively have a higher precision on some of the terms like advection. Okay, and MIT GCM uses the same Araka C grid as well, and probably oceanograms as well. Okay, and what defines a lot, so the difference between ocean models is often defined by the vertical coordinate system. So for ROMS, we're using a terrain-following Navier-Stokes equation. So on one hand, you have the continuity equation, means that mass is conserved, or the Gaussian approximation volume is conserved. And then you have also the conservation of momentum. So the typical force equals mass times acceleration. But for fluid dynamics, in the form of the Navier-Stokes equation, which tells you that the acceleration of the fluid can only be due to a force like the advection, Coriolis force, or pressure gradient, or other forcings or diffusion of momentum. Okay, and similarly for the for any tracers like temperature and salinity, you have this tracer balance. Okay. And so, yeah, let's start with the with examples. So everybody should have a username password, which is written down on the sheet of papers. And if you're following online, on the ROMS.gl website, there is also a virtual machine pre-configured with all the software, but there's also detailed instruction how to set up your machine if you use a Linux machine. Okay. There are a lot of small improvements that are made to ROMS.gl recently, and it's in branch ROMS-4.1, and so that's the branch that we will be using. But if you're using the server, you don't have to worry about this. Okay, everything is already pre-installed there. Okay, so it's quite important that every user use a different user account. So if two people try to modify the same notebook, that won't work very well. Okay. So this hands-on session is we have 4 notebooks that I want to cover in this hands-on session. So these 4 notebooks are already available within this the common repository for the Air Center, but you can also download it here. So I have also put a link here. Okay. So these are the 4 notebooks that we're covering. So first, building ROMs, preparing all input files, running ROMs, and then making some plots. Okay. So these are the 4 notebooks that we need to download. Okay. And then once you have downloaded all the notebooks, let's go to this Jupyter Notebook server. Yeah? Okay. Yeah, you have to upload it yourself. Yeah, exactly. Yeah. So maybe. You're not using the server, right? Not. If you have the error ROMS.build undefined, you should check out the. You're not running on the server. You're running locally.
I'm running on the server.
Then okay. Okay, sorry about that. Then I think you have to restart the server. So if you restart your environment. So if you have this, go to Hub Control Panel. Stop server. So I will also stop server. Oops. And oops. Okay. Who's running? You're running one? Oh, sorry, I stopped your server accidentally. You're on 100. Okay, let me take another one. Oh yeah, let me just take. Okay. P. Okay. Okay. So something to check is that you should indeed all have Julia 1.11. If you see 1.10, then you probably have to stop the server and restart again, and then you will get the new version. Okay. So to stop the server is you have to go here in the hub control. And then you have the option stop the server. And then when you relaunch, you should get Julia 1.11. Yeah. Okay. So everybody got Julia 1.11? Yeah? By now? Okay. And so the next step is now to upload all the notebooks. Yeah? The upload button is actually this button here. So click on this button, and you can select multiple files, no problem, and just upload the 4 notebooks to the server. Okay. And then just click on the first one. And if there is any questions, anything that is unclear, or any issues that you have, please just ask. So don't wait, just ask right away so that we can have your questions when they arise. Okay? So who was able to open the build ROMS notebook on Julia 1.11? Can you raise your hand if it's okay? And who tried is not, who had some issues? So everybody. Yeah, I'm sorry. I updated the Docker images recently, and if the Docker image was already used before by somebody else, it didn't use this latest version of the Docker image. That's the reason why some of running an old version of the Docker image, but here. But if you have Julia 1.11, it should be okay. Okay. So let's just run everything here, and then I will walk you what we are doing. So select on run all cells. Yeah, sure. Okay, run all cells. And so the first thing that we're doing here is actually getting the source code of ROMS. Okay, so and ROMS is by now distributed over GitHub. So we're just cloning the repository and using the latest version, which is ROMS 4.1. Okay. And as we're making a checkout, Git will tell you that we are in a detached head state. So the students are sometimes a bit worried about this, but it's not an error message. It's just a normal Git terminology. Okay. And so ROMS is a source code, like traditional source codes which are compiled in advance, and then you have to specify what option do you need in ROMS. Okay, so this is done through a header file, and there you have to define different options in ROMS, what kind of advection scheme you need, what kind of pressure gradient scheme you need, and this is defined in a header file. that we're giving here the name ligurancy.h, because in our test case we are looking at the ligurancy. And yeah, these are the different steps, that's different parameters that we activate into ROMS. Okay, so when we're running this cell, it will just create a file on our disk called ligurancy.h in the directory model dir, and it will just activate all this option that we need. Okay. And the next step is actually to tell how we want to run ROMs. Do we want to run on a single CPU? Do we want to use multiple CPU? And if we use multiple CPU, what kind of scheme that we're using MPI, the message passing interface, or using OpenMP multiprocessing. Okay. So since we are here on a single node, it's easier to use OpenMP. So we don't use MPI, but we use OpenMP. So we're setting use OpenMP to true. Okay. And then the next step is actually to build the ROMS source code. Okay. So we're calling our application ligurancy. We're using the G-Fortran compiler, and we're using two compile jobs. We can even use more if we want. And then all the compilation will not, per default, it will be just printed out in the output cell, but it's a lot of text. So we are capturing the output into a log file. Okay. So this will then compile ROMs into a binary. Okay. And what we see later on is then just, instead of showing the all compilation log, I'm just showing the first line and the last 5 lines here. Okay. So typically, what you need to change for your own applications are rather this header file. So if you use a different application, then maybe you would want to use a different turbulence scheme. So that's typically the header file that you need to change.
In order to comment out to double hash, or is a hash already a comment out? So you define.
Actually, this is a long string.
Yeah, it's a long string that you are printing into the ligurancy.h.
Uh-huh.
But in the ligurancy.h, if you want to just leave it there, but you don't want it to use, is it a double hash?
This is you use the normal C syntax to comment. So if you want to comment this out, you would just put this in front and this behind. So this will comment it out. So that's a bit. So the preprocessor uses the C commenting rules. Okay. And so, so if compilation succeeds, it should build like this ROMS library, and you should have no errors. Okay. Can you show a hand who has some problems to build ROMS, or is still running ROMS, still compiling ROMS? Okay. Okay. Did you check that you have Julia 1.11?
Yes.
Okay, that's good. Okay. So now, if this works fine, let me show you already the next notebook. That's a preparation of the input files. Okay. So to make it short, to make it the test really quick and short, we're running a fairly coarse resolution model, and just for 3 days, just to test if everything works fine. Yeah. And then if everything works fine, then we can crank up the resolution and also consider longer time steps. Okay. So the first thing that we need to do is actually to download the bathymetry. Here we're using the JEPCO bathymetry. So as before, let's run all cells, so that to be sure that everything is ordered, is run in the right order. So the first thing that we do is to download the JEPCO gap cobathymetry because we will need it to define the bathymetry depth of the ocean. Okay. And so, if any term that might sound you unfamiliar, please let me know. This hands-on session can be as interactive as you would like. Okay. So we're defining with T0 and T1 the time range of our simulation. So we are here just simulating 3 days for start. But later on, when it works fine, you can try to use longer time frames. So that's just a quick test. Maybe let's test for 3 months or something. 3 months. Okay, but let's just use just a couple of days to make it quick. Okay. The next thing, you have to specify where in the world you want to simulate. So typically, this setup assumes that you're not running a global ocean simulation, but rather a simulation of a limited part of the ocean. So a regional model setup, and most of the case in ROMS you actually do run regional setups. So defining the longitude and latitude range where you're simulating. And this area corresponds to a part of the Mediterranean Sea, which is called the Ligurian Sea. Okay. We're not using the resolution of the bathymetry as the resolution of our model. We are degrading the bathymetry because the bathymetry is a bit too fine. So we are degrading the bathymetry by a factor of 4 in the two horizontal directions. But if you want to have a higher resolution, you would need to reduce this degradation. So here we use 4 by 4, but if you use 2 by 2 or 1 by 1, it will be you will have a higher setup. Okay. And in ROMS, as ROMS is a terrain following coordinate system, yeah? Simone? Actually, the gap cobathymetry is as a resolution which is 30 seconds, 30 arc seconds, but this is too high, so we're degrading by a factor of 4. So it's 4 times 30 arc seconds resolution. Yeah. So it's easier for me to have the bathymetry, and then I tell you by how much did I need to aggregate the cells to have the model bathymetry. Yeah. Okay. And the next thing that we need to define is the which kind of vertical transformation, which kind of vertical grid, vertical coordinate system that we want to use. There are several implemented. So I think this is the default one, but it's you can also experiment with different ones. But it's quite important if once you change this the vertical resolution, you have to update all the initial conditions and boundary conditions in order to match your new vertical coordinate system. Okay, and we have here 32 levels. And the theta S and theta B are 2 eight-dimensional parameters which allow us to refine the resolution near the surface or near the bottom. Okay.
So you fix so again, sorry, so you fix the line that that's the T line, right?
So the T line is just a parameter, so the typical thermocline depth. But it's not fixed in the model, but it's typically where you expect the thermocline to be. Yeah? But it can be at a different depth.
So it's basically like
It's really only for the coordinate system, okay? And so you want to have, within the thermocline, you want to have the layers evenly spaced, okay? More or less evenly spaced, okay? So it tells you here that, okay, let me give about evenly resolution at the first 50 meters, and then do something else below, okay? Yeah, it is a variant of the sigma coordinate. It's a variant of sigma coordinate. So it's not exactly sigma coordinate. You can put it to be exactly sigma coordinate if you would put t-cline to 0, for example. Okay.
To do something specific for the upper part,
Yeah.
then it will sigma.
Well, it is a continuous function, so it's not if up or if then or if lower. It is a continuous function, but it has the traditional sigma coordinate as a special case, but it allows you to distribute the vertical layers a bit more differently near the surface.
Is that equivalent to the hybrid components that are used in weather models? Starting straight following and then they become pressure coordinates.
It's similar, yeah. But it's you can be hybrid in so many different ways, but it's probably similar in spirit, yeah.
It's free surface following at the top.
Yeah, exactly. So the top layer would be exactly the free surface, and the bottom layer would be exactly the ocean floor, and then these parameters tell you how to distribute the resolution in between. Okay, so we're generating our topography and effectively generating our model grid using this. And we always, in ROMS, we have to smooth the bottom topography. And that's the Rmax parameter for, which controls how much you smooth it. And so you get, it will tell you also how the different layers are distributed vertically. Okay. The next step is to define the to take, in fact, a large-scale model, a global GCM, a global circulation model, or a regional circulation model, but which includes your model, and here we're using the data products from CMEMS, which has different models for Europe, and also a global model. And in our case, we're using a particular one, which is mentioned here, if you are interested. So that's the model from CMEMS that we're using. It's a Mediterranean model, and from this model, we are actually extracting our initial boundary conditions from. Okay.
So it's not free boundary conditions, is it? You are imposing the boundary conditions.
Exactly. You're imposing the boundary conditions using another model. Okay. And you have to just so every data set sometimes have different conventions, different naming. So you have to say, okay, if I need to have seawater salinity, I have to look to this data product. If I need to have potential temperature, I need to look at this data product. So that's just a mapping between the names from the climate forecast convention and how they are named in the CMEMS. Okay. And then it actually creates an object, a dataset object, which represents the dataset on the ZAR data store from CMEMS. And then when you're interpolating this circulation model, then the data will actually be downloaded. Okay. So ROMS calls this CLIM for climatology, but it's maybe for historical reason, because the first nesting was done actually with using climatology, but now most of the case, the boundary conditions do not come from climatology, do not come from a mean state of the temperature salinity, but rather from another model. But it's still called CLIM in the context of ROMS, and I named my function similarly. Okay. So you're interpolating the model state on the ROMS grid, and then you're extracting the initial condition and boundary conditions. Okay. And in this case, this will actually download all the data for you and make the interpolation. And actually, when you have quite a large setup, this interpolation already can take some time. And so this code actually can benefit from also, this is also parallelized and can benefit from more CPUs. So this is a really small test case, but if you want to have larger test case, you can change the kernel. So there's one kernel with 4 CPUs, so you can use this as well to speed this up, this interpolation. Okay. We are also nudging at the edge of the boundary, and that's another netcdf file that we need to create for the nudging. So essentially, the boundary condition tells ROMS how it should behave really exactly at the boundary, yeah? But the model is free to do what it wants inside the model domain. But sometimes it's useful to also to pull the ocean models towards the boundary condition, also slightly off the boundaries. Okay, and this is due to this can be easily done with nudging. Okay. And the next step is to prepare the atmospheric forcings. And for this, we use the ECMWF operational archive. And so I already prepared for you the data file, which you can, which is then automatically downloaded in the notebook. And there's also some transformation that we need to do in order to convert all the parameters that would be necessary for ROMS. And here, ROMS actually does not need to use, in the present configuration, ROMS does not need to use all these variables, like the wind stress, but I prepare them anyway, because then they are also available if you change the different formulation into ROMS. Okay. So essentially what ROMS needs, for example, the wind at 10 meters height, yeah? And from this, it computes internally the wind stress. Okay? But it can also use directly the wind stress from the atmospheric model. Okay? But most of the time, it's actually better to use the wind field and then let the ocean model compute the wind stress. Okay? So we are just preparing the wind stress, but it's actually not used. Okay. So this goes through all the dates and interpolates them and prepares them for a ROMS simulation. Okay. So ROMS is actually one of these models that was mentioned before that is actually configured to a text file. So you have to tell ROMS where to find the different netcdf files. And this is done via a configuration file. And here, the next cell tells you actually what kind of change you need to do. Okay. So typically, if in the ROMS configuration file it asks for a grid name, yeah, we just prepared this netcdf file previously, where with the ROMS grids. If it asks for an initial condition, this is the thing that you need to put there. Yeah? And if it asks for boundary conditions, the boundary condition file was named like this. So you already know now what kind of changes you need to do in the text file in order to run ROMS. Okay. And these are all the forcing variables. Okay. But since editing these text files could be a bit tedious, I also made some code here in these Jupyter notebooks, which substitute all these keys automatically in the text file, so you don't have to do this change by hand. Okay. So essentially, this is what we're doing later on here. So we substitute in these text files all these names of the netcdf files. Okay. And something else which is quite important is you need to tell ROMS how to split the domain. Okay, so you need to tell ROMS how to split the model domain, and here we set n-tile I and n-tile j equal to 1. Okay, so it means that we're just using one CPU. But if we want to use more than one CPU, let's just put n-tile I and n-tile j equal to 2. Okay, but later on, when we're running ROMs, it is important that we remember that we need to run ROMs on 4 CPUs. So let's just decompose our domain into four tiles. So any 2 by 2 tiles. Okay. So if I change this, and then this will be changed. So the output of this ROMs in file replace, it actually tells you all the changes it made to the default configuration file. Okay, so the default configuration file has a title called mytest. Okay, wind-driven upwelling, and we just change it to mytest, and then we change the grid size, we change the number of tiles, and so on. And we also changed which boundaries are open, which boundaries are closed. Okay. So let me just here. Okay. Let me just show you. So this is the model domain that we're looking at. That's the bathymetry of the Ligurian Sea, and we see that we have one open boundary to the west and one open boundary to the south. Okay, and the other 2 boundaries are actually closed. And that's something that is mentioned here in this this configuration file. Close this. Okay. Okay. So for now, everything was. So I think you don't need to change anything in these notebooks, but if you want to use more than one CPU, you can set n-tile I and n-tile G to maybe 2 by 2. Okay, so that means that you're using 4 GPUs, but we are running all on the same machine. So please do not put 100, everybody. So that would be a bit too much. Okay. So, but there are quite a lot of proc. Just yeah.
If for in I will just think hypothetical. If we want to run a particular region above down here, you said that we should change well, if you want to run for a different region, we need to change the product ID and the connecting ID, but we need to get those of the Copernicus data store and which product do you use?
So if you're running a nesting in the Mediterranean Sea, you can use the data product that I'm using here as well. But the data product that I'm using covers only the Mediterranean Sea. So if you want to simulate an area in the Atlantic, you cannot take the initial condition from the Mediterranean Sea. So you just have to then use a different parent model for your boundary conditions. Okay. A parent model, a larger scale model. Okay. So what we are doing is kind of the child model, yeah, the nested model, and it takes boundary conditions from a larger scale model. Okay.
Yeah, but where do we get that those boundary conditions from? Because you are downloading them from the company website, right?
So we're downloading it from CMAPS, yeah, but CMAPS runs different models. So one model is from Mediterranean Sea. You have in CMAPS also a global model, okay. And you can also use HICOM, for example, for the boundary condition. HICOM is also another global model where you can extract the boundary condition from. Okay.
So basically, there will be analysis basically.
Hmm?
global ocean physics pre-analysis.
Yeah. Yeah.
Okay.
So essentially, you're telling the script which boundary conditions, which is the data source that you want to use. Okay. 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 So now let's run ROMs. Okay. So per default, it uses just one CPU. I changed before entile I and entile j to 2. Okay. So it will use 4 CPUs now. So you have to be consistent. If you change it in one notebook, you have to change it in the other notebook as well. Okay. And then it will launch your model simulation, and it will use OpenMP in order to spread our workload. Okay. So let's here select run all. And then if you're in a terminal, you should see now ROMS O running using about 400% CPU because it uses four CPUs. And then it will just run and create the model results. Okay. So run ROMs. So if you're using MPI, you sometimes have to specify, you sometimes have to unset this variables opal prefix, which conflicts with the MPI OpenMPI implementation used. Okay, but actually for OpenMP is not strictly necessary. Okay. So typically, you're not running ROMs really from a notebook. Typically, you're running ROMs rather from a terminal. And if you use ROMs via MPI, it's a classical MPI run or MPI exec command with a number of processors. It's the only input argument you're giving the configuration file, where you are specifying all the netcdf, which netcdf files to use for the bathymetry and for the boundary condition and so on. And if you're using OpenMP, you typically set the environment variables, a variable OpenMP num threads to 4 if you're using 4 CPUs. Okay. Okay. So you can also inspect in the terminal what we are doing now. So if you go on launcher and open a terminal, yeah, there should be a directory which is called ROMS implementation test. So that's our particularly ROMS implementation. These are all the netcdf files that created during setup, so initial conditions, boundary conditions, and so on. And our first simulation is in simulation 1. Okay. And this is the output of the ROM simulation. Okay. So we started creating the input files, roms.in, and then when ROMS was finished, it created the ROMs result as netcdf files and also the ROMs out. Okay. So this is typically the output of a ROM simulation. It repeats all the input parameters that you gave to ROMs, and then when it runs along, it tells you some basic statistics about the model simulation, like kinetic energy and maximum velocity and things like this, to see if when something goes wrong, you can easily see why is this the case. Okay. So this was a really quick simulation because we are just running for a really short period of time. Okay. Any questions so far? Or any errors while running ROMS? So everything worked fine? Okay. And now, once this is done, we can plot the results. So actually I have two plotting notebooks. So the one that you have here, the 04 is using PyPlot for plotting, but there is also a 05 on the web page that uses Maki. Okay. So as before, let's run all the cells. And then we can have a look at the bathymetry. So it is a smooth bathymetry, it's not the original Gepco bathymetry. And so it essentially tells you the depth. And what you can recognize here, that's the Corsican Islands, France, Italy, Elba. So that's the domain that we are looking at. So we can plot our initial condition by setting n equal to 1, or if we can plot later on, we see how the temperature evolved over time by using different values of n. Okay, so ROMS uses per default or uses the format netcdf quite extensively, and we can have a look at. So this is a typical ROMS output. So one of the nice things of ROMS is that it's really extensive. So in the output, you find a lot of information about your actual input that you choose in order to run ROMS. So later on, if you have a great simulation, but are not sure exactly what kind of parameters that you use to make the simulation, ROMS helps you a lot by documenting all this information inside the netcdf files. And yeah, so it outputs a lot of information, but typically what we are interested in are in the parameters like zeta, which is the free surface elevation, u bar, v bar are the barotropics, meaning depth aggregated velocities, u and v are the full three-dimensional velocities, w is the vertical velocity, and so on. And temperature, salinity, and so on. These are the main variables for model simulation. Okay. And the next plot shows temperature and currents together, which tells you which shows how well they are actually related, temperature and currents. And this is due to the geostrophic balance. And if you want, you can try to plot different time instants, for example. Okay. When you compute, you can also, here in this notebook, you can also extract the model simulation along a vertical section. Well, this is very important that you use exactly the same parameters of the vertical coordinate that you actually used ROMS to configure. So here, this is a north-south section, the first 300 meters of a north-south section of the ROMS output. And later on, we have here a horizontal section. Okay, so if you're looking at the ROMS output at the horizontal section, say 200 meters, you have some areas which are blank, which simply means that these areas are not as deep as 200 meters. Okay, so it's quite normal that you don't have a value everywhere. Okay. And the last visualization here is arbitrary vertical section. Yeah, so what is quite interesting, so we know that here in this area, there is a current that we call the northern current or the Ligurie-Provençal current, which is quite strong current in this area. And it is quite useful to make a transect perpendicular to the current to have an idea about its vertical extents, for example. And this can be simply done using the interpolation package, where where essentially you're extracting for every layer the corresponding value to make this kind of plots. Okay. Okay, so did it work for everybody? Yeah?
Just a question on the atmospheric forcings, the forcings that we downloaded, are they specifically for this, as in, did you download, is it for a slightly wider region, or is it specifically tied to this specific grid that?
You mean the atmospheric forcings?
Yes.
Yes, it is for this grid. Yeah. You can because it's really it would be really big if it's for another area. So I only prepared the atmospheric forcing for this, the ECMWF forcing for this. But the format of the ECMWF file that I use here is the same that you get when you download it from ECMWF directly. Okay, but there would be an additional step if you use a different area to get the ECMWF forcings. Okay. If you use a different area, there are a couple of things that need to change. You need to have a global bathymetry, okay, not just a bathymetry of Ligurency. You have to use the ECMWF forcings. You have to download yourself the ECMWF forcings, okay. And another thing that you need to adapt is which model that you're taking the boundary conditions from. Okay, so these are the three things that you will need to adapt if you use a different domain. Yeah. Yeah.
Do you think there's generally scope to streamline all of this? I mean, obviously we want to appreciate all the efforts to translate, provide a Julia interface to all of the settings that does a quadrant model ROMS specifically thing. But do you think there's because a lot of these options, it might be nice that you can choose them if you want to, but from a first user completely hide those and just say what's hidden in the using whatever package name enter, hide a lot of that also constellation in that. Do you think there's scope for that?
Yeah, interesting question. So when I started with this, I really did not initially do a new interface to ROMS. So I wanted to just have something for my students that they can easily set up, prepare all the input files that they need to do, that you have to do it anyway. Okay, and then when you run ROMS, you have to take a text editor, edit this configuration file, put the right file names, put the right parameters. So that was the kind of original idea where I came from. Actually, initially I tried to avoid to create a new interface for ROMS, because if you have a problem, it helps to know, it helps to communicate with other people that do not use the Julia ROMS package. Okay.
No, absolutely agree with that. I just think see one example of how to run a GCM in 11 lines of code, and the old dusty Fortran interface is obviously miles in between. And you're creating something in between now. I absolutely agree that creating a new interface is a very challenging task, especially if people don't want it to be too restrictive but still want to hide. It's a lot of choices that you have to make that are probably difficult. But I was just wondering whether there's scope for having something, even streamlining that more.
Yeah.
Process is not so, at this point should not so much be the pre-compilation of the model, but rather
Hmm.
more,
Yeah.
what would make things more user friendly at this stage?
Well, the easiest thing is indeed if you use directly with global products, yeah, like the global Siemens model or the global HICOM model, which is also quite high resolution. So if you use the global HICOM model, then you can use it for any domain. So that you can just you can nest directly in HICOM, and then you don't need to worry about which large-scale model that you're using.
But it's like the thing right now that I'm facing is the atmospheric forcing,
Mm-hmm.
which there are ways to streamline the downloading process for the atmospheric forcing for ECMWF, especially if you're using reenact data that have been incorporated into ROMS.jl.
Yeah, yeah. So currently for this one, I'm using the operational archive for ECMWF, and yeah, and that's something that you need to ask permission to your weather service to get access to this. So I didn't see that much value to simplify this process because maybe not everybody has access to this data. But there are data sets from ECMWF, like the ERA 5 data sets, which is quite easy to access. Yeah. Okay. Okay, well then, I think that's all for me. So if you want to play around with this, maybe like make a longer simulation or make a higher resolution, so don't hesitate to do that. If you change something on the notebooks here on the server, do not forget to download all your work. Yeah, download all the notebooks, because once you're hitting on stop server, everything gets deleted. Okay. Yeah.
So this simulation was about like 200 cells, 200 times 50.
Yeah, 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 yeah.
Like for 3 days.
Yeah, really short.
What's ready to run a maintained simulation? Roughly, what do you suggest?
What do you say? What
To run a simulation on the whole Mediterranean Sea.
for the whole Mediterranean Sea?
Yeah, how much resources would you
Just on the top of my head, I would use maybe 64 CPUs or 100 CPUs. So I think that's yeah. So it should not that be difficult. Okay. Well then.